Okay, so this is the equation, linear equation and rotational equation. Okay, so the first equation, this one we will look at it later, yeah? Okay, so the net force applied on an object in order for the object to move equals to the mass times the acceleration. So when it comes to rotational motion, the net torque applied on an object for it to rotate is equals to the moment of inertia kg meter squared times the angular acceleration. Okay, so how fast an object is spinning is actually depending on the moment of inertia and the angular acceleration that you apply on it. Okay, so this one you have already looked at it in your first semester, the most common kinematic equation. So in kinematic equation, you use these two, right? So if you have to apply it in rotational motion, what you have to do is you just have to translate the linear quantity into the rotational quantity only, right? And last one, this is the kinetic energy. So kinetic energy for any object is given by half mv squared. So this is rotational. I put a R in front, means rotational kinetic energy. So rotational kinetic energy is given by half I omega squared. So it's actually in line with the translation, yeah? Just now when we look at M here, it's translated to I, right? Your V here is translated to omega. So that's why rotational kinetic energy is also equal to half I omega squared. Okay? So now let's look at the first part, which is moment of inertia. Okay, so the moment of inertia is equivalent to the resistance of an object on any rotating effect. Okay, the resistance of object on any rotating effect. Okay, so just like the example that I've given just now. Okay, let's say you have a ping pong ball and you have a bowling ball. Which one do you think will have higher moment of inertia? Ping pong or bowling? Ping pong or bowling? Ping pong. Ping pong? Higher moment of inertia. Bowling, right? Yeah, because moment of inertia here, okay, is equal to m times r squared. It's depending on the mass and also depending on the radius. So radius here refers to the center of rotation, right? So let's say now if we look at the ping pong and bowling, yeah? Okay, so these two, which one is heavier? Bowling, right? Bowling has higher mass. Okay, the center of rotation is similar at the center. Okay, so now here we know that bowling has higher moment of inertia. Okay, so now if I want you to spin these two balls with just two fingers, your thumb and your pointing finger. Okay, which one is easier to be rotated? Bowling again? Bowling. Bowling again? And you're ping pong ball, right? If you can you easily spin the bowling ball with just two fingers? Cannot. Okay, it's very heavy. Okay, so because bowling has higher moment of inertia, that's why it is harder to be rotated. Okay, but your ping pong is easier. Right? So same goes if now these two balls they are actually spinning now. Okay, so if I want you to stop them, yeah, I think I need you to mute your microphone. Okay, so if I want you to stop the ball with your pointing finger only, see which one is easier to be stopped now? It's ping pong ball again. Okay, the one with higher moment of inertia kind of like will resist the change. Either it is rotating or you want to be rotated. Okay, so it's actually similar to the linear motion, the inertia in linear motion. So an object when it is moving will continue to move. Okay? Or an object when it is at rest, it will continue at rest. Okay? Until you apply another force on it. So same goes with moment of inertia. If an object it is not spinning, so it is harder to be spin. So if it has higher moment of inertia. Okay? So what I want you to bear in mind is whenever it is about moment of inertia, okay, it is actually similar to inertia, but it's only applicable to the spinning effect. Okay? So the common equation for moment of inertia is given by I equals to mr squared. Okay? So that is the common equation when no shape is mentioned. But if the shape is mentioned in the question, okay, so you can actually refer to the chart here. You can refer to the chart here, yeah? This one. Okay. So in your syllabus, the one that usually been asked is a solid cylinder, hollow cylinder or hoop, solid sphere, and hollow sphere. So these are the four common shapes that will be asked during your exam. So if the shape is given, you don't have to use I equals to m squared to find the moment of inertia. Instead, you can actually just directly use the formula given in the chart. Okay? So this is in line with the Newton's second law, F equals to mf, vector net force equals to m times a. So same goes with rotational motion. In rotational motion, net torque is equals to moment of inertia times the angular acceleration. Okay, moment of inertia, kg m squared, angular acceleration, radians per second square. Okay, next page. So rotational kinetic energy. Okay, so what is rotational kinetic energy? Rotational kinetic energy refers to the kinetic energy used by rotation only. Okay, so let's say if I have an object, a boxer, which is sliding down the hill. Do you think it has rotational kinetic energy? No, right? Because no rotation is happening. But what if I have a ball which is rolling down the hill? Yeah? So it is going down the hill. The direction of the movement is linear, going down the hill, but at the same time, it is also rotating. So the energy that used for the ball to do the rotation is what we call as rotational kinetic energy. Okay? But the linear motion, when it is going down the hill, this one is counted as normal kinetic energy, which is half mv squared. But rotational kinetic energy is given by half I omega squared. Okay, so let's look at a simple energy system. If I have a ball, okay, rolling down the hill like this. So what are the energy that I have in this system? Okay, so the first one, since it is not on the ground, yeah, it's somewhere hanging in the air. Okay, so we have potential energy here. So as it is rolling down, rolling here, tells you that it has rotational kinetic energy, right? And since the ball is going on a linear motion in this direction, so here you have another kinetic energy. So if we combine all this energy here, so we will have a total of potential energy plus translational kinetic energy plus rotational kinetic energy at this particular point. So I want you to recall, what is the formula for potential energy? Anyone wants to write your answer?
MGH.
MGH, very good. Okay, is equal to MGH. M is the mass, kg, G is gravity acceleration. So in your syllabus is 9.8 times, 9.8 meter per second square. H is the height, which is in meter. Okay, what is the formula for translational kinetic energy? Half m e squared. So m is kg, v is velocity in meter per second. Rotational kinetic energy, half I omega squared. So I is rotational kinetic, moment of inertia, kg meter square, and omega is angular velocity, which is radians per second. Okay. So the energy system, according to conservation of energy, right? In this case, we will always assume friction is negligible. So according to our conservation of energy, total energy initial is always equals to total energy final. Okay, so we can actually find all the property by expanding the equation into Ke plus RKe plus Te. Okay, so we will have the example of calculation method. Yeah? Now the last part of the topic is angular momentum. Okay, so angular momentum is given by L and is calculated by moment of inertia times angular velocity. Okay, so according to the conservation of angular momentum, the total initial angular momentum is also equal to the final angular momentum. So that's why we will have I omega initial equals to I omega final. Okay, so I want you to try the question here. So I give you 3 minutes. Okay, no matter I will write the answer here. You all try first. If you have any question, you can always ask it. So you are free to open your mic now. So revolution, since this is not in SI unit, right? So if you want to convert to SI unit, this one you will learn in your chemistry soon. Unit conversion. So 0.8 revolutions per second. So you can, if you want to cancel off the revolution, so times with the same value. So 1 revolution equals to 2 pi radian, isn't it? So double check, cancel off revolution here. So left only 0.8 times 2 pi radians per second. Okay. So this is how you can do your, instead of memorizing it, revolution to radians is times 2 pi, radians to revolution is divided by 2 pi. Instead of memorizing like that, you can actually use a technique. Okay? As long as this one 2 pi radian divided by 1 revolution is equals to 1. So 2 minutes from now. Maybe you have to put it like this. Okay, I put like this. Going down like that. And down. Ada participated or no? 22 out of 46 or 20 plus. Okay lah, 20% lah. It's enough to be considered. No, we have already from like 40, 40. I have to do the notation. What is the Wi-Fi? Bye. 2 minutes mà, 2 minutes là hộ. I'm actually recording using share and everything is white. I don't care now. I'm tired now. But you just like, I don't know why I so long doesn't look. Yes. Okay. So, part A. So I scatter here 0.8. This is your initial angular velocity with her arm extended. So she has a moment of inertia of 4.34. Okay, with her arm. So if this is your eye scatter, okay, so the arm is extended. So this is initial. That is the initial moment of inertia. So after that, her arm is close to her body. So arm close. So that is final. 0.363 is the final moment of inertia. Okay, so what is the angular velocity in revolutions per second after she pulls in her arm? So applying conservation of angular momentum. Total I initial omega initial equals to final I final omega final. Okay, so plug in the value 2.34, initial omega is 0.8, final 0.363 times your final omega. Okay, so in your calculator 5.16 revolution per second. So you don't have to convert the units first, because in the question that requires you to write your answer in revolutions per second. So now, what is her rotational kinetic energy? So rotational kinetic energy we know is given by half I omega squared. Okay, so before and after means you have to find both initial and final. So initial, half I initial is 4.34. Omega 0.8. So what else you need to do here? Okay, bear in mind this one, the calculation here is in SI unit. Right, for energy is in joule. So when joule is in SI unit, all the quantity that you plug in here has to be in SI unit as well. Okay, so 0.8 revolution per second convert to radian is equals to 2 by radian divided by 1 revolution, right? So cancel off. Right. Yep. So what you get? 29.6 joule as the initial rotational kinetic energy. So final is equal to final moment of inertia times final angular velocity. So you get 191. So are they the same? No, right? So does it mean that it is not following the conservation of energy? It is actually following. Okay? So this is the part that always students will get confused with. Conservation of energy, okay, is referred to as the total energy, the total mechanical energy. Okay, it doesn't refer to as one form of energy only. So when I say the initial energy is equal to the final energy, it must be the total initial. The total here is very important. The total initial energy equals to the total final. So final total energy. Okay, but if now if you are only referring to the rotational kinetic energy itself only, it will change. Okay, so if you look at here, from initial to final, which one do you think will move, will spin faster? Initial or final? It's definitely final, right? If you look at the velocity, the angular velocity, okay, the final angular velocity is much faster than your initial angular velocity. So that's why your final rotational kinetic energy is faster because it is rotating faster. Okay? So any question about the notes? If no, then we will proceed to our tutorial workshop now. So I want you to open your tutorial workshop. Do you know where to open your tutorial workshop? Okay, again, it's on your Moodle page. 1B here, this is summary notes. So the next one, click on this one to download your tutorial workshop. Okay, so look at the first part. So the first part here, it's about torque and moment of inertia. Okay. So I want you to look at here. Do you prepare the stick and the cone? you see my tip and turn? Yeah. Answer yes, but if you have something to lock at the side, otherwise it's difficult to find to test the power of moment of inertia. This is another one. This is my laptop fall down. I focus on that. Okay, so I just want to show you here. Okay, this is a stick where I load the coin at the end of both sides. Okay, so if you look at here, this is actually 5 cents coin. Okay, so I load the 5 cents coin at the end of the stick. And another one I prepare with 20 cents. Okay, so the 20 cents, instead of I load it at the end, but I load it near to the center. Okay, and this point will be my center of rotation. Okay, so I want you to guess. Comparing these two sticks, 5 cents and 20 cents, if I want to spin, okay, at this center of rotation, okay, turn back and forth like this, which one do you think it is easier and lighter for me to spin? Let's see if I can ask you here. Can you hear my spin just now? Okay. Yeah. This is my 20 cent stick where I load my 20 cent near to my axis of rotation. Okay. And this is my 50 cent stick. Okay. So sorry, not 50 cents, it's 5 cents only. 5 cents. So I load it at the end of the stick on both sides. So if I have to place them back and forth at the center of the stick as my center of rotation, like this, which one do you think is easier or lighter for me to rotate? Okay, so let's see if I can ask you all to forward. So which one do you think is easier to rotate? And I let you all to choose. Okay, y'all can choose from here. 5 cents is at the end, and this is my center of rotation. 20 cents is near to my center of rotation. So which one do you think is easier for me to locate? If you have something else, let's say if you have pencil, or you try to hang something at the end of the both side of the pencil, or if you want to use one side, you can. Okay, you have to hang something heavy here, attach something heavy here on one side. So one you attach it at the end of your pencil, another one you put it near to your pencil, and you try to spin. To see which one is lighter for you to spin. $0.20 is heavier than 5 cents, right? But now they are located at different positions of the stick. So will it change the result? No. Okay, 2 minutes is over. So now let's try. Okay, so what I want to do is if I bring them to and forth for 20 times. So can someone help me to count? Count the timer. Okay. We'll start with 5 cents first. Since everyone, most of you voted for 5 cents. Okay. So 20 times. Okay. 1, 2, 3, start. 1, 2, 3, 4, 5, 6. Okay. How long is it? Okay. This is what happens when it is online. No one is helping. Is that right? No. I need someone to help me to count 20 times and record the time. The timer starts here. Start here now. 20 seconds. No, I will turn back and forth for 20 times. And stop. So I will count here and it will start here. Okay. So again, 3, 2, 1, start. 1, 2, 3. Come on, my screen. Here. Okay. So start, yeah? 3, 2, 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. 20. How long? 8.85. 8.58. I'm sorry, 8.58. Oh, by the way, my housemate is... Oh, thank you. Thank you, Edison. So my housemate is Miss Edison. If anyone is doing in the class, so you have to understand the opportunity. Okay, so now we try for the 20 center. Okay. Again, yeah. This is experiment. Okay. This one will start from 3, 2, 1. Okay, 20 already. 6.52. Yeah, 6.02. Okay, thank you, Edison. Okay, so now if you have trust, you can try it at home. Try to look something. Okay, even though 20 cents is somehow heavier than your 5 cents, but what happens is okay, but what happens here is because your the center of gravity, the center of rotation is different, which makes your radius different. Okay, so let's refer to the answer just now, yeah? Okay, so we have already measured the width, yeah? Okay, so what happened is we have two samples just now, right? Sample A, in which it's 5 cent coin, which is loaded at the ends of both sides. Okay, so it's actually two 5 cent coins on each side. And we have another one, which is sample B. With 20 cents, which is our center of rotation. 20 cents located on each side, but it's somehow near to the center. Okay, so the mass of 5 cents, mass of 5 cents, we have already measured is 1.75 grams. Very light, right? And mass of 120 cents is 5.63 grams. Okay, so look at here. Even though the mass for 20 cents is heavier, but according to the time just now, sample A, how long did we take? Around 8 points. 8.49, 6.02. Alvin, I will answer your question later, yeah? Okay, so sample A takes longer time. So why is it so? Okay, so what I want you to do is now we calculate the moment of inertia of both the samples. You can delete column C, yeah? Because we have only two samples here. Okay, so how do we actually calculate the moment of inertia? Okay, so moment of inertia is equals to total moment of inertia equals to m times r squared. Okay, or you can actually write as total m r squared. Okay, so what is your m? If you still remember the questions in your lecture notes, okay, and this is your center of rotation. Here is your m1, isn't it? That will be your m2. So the distance between the center to your m1 is considered as r2. The distance between the center to your m2 is your r2. Okay. So for sample A, okay, wait, we come back here. So total I equals to total m r squared, so it's equals to m1 times r1 squared plus m2 times r2 squared. So m1 is your M1 on one side is given by two 5-cent coins. Okay, so 1.75 times 2 gram convert to SI unit, so times 10 to the power of negative 3. Oh, my surface a bit. This is over. So convert them to SI unit, becomes 3.5 times 10 to the power of negative 3. Okay, so M2 is the same because the same 2 5-cent is on the other end. Okay, 3.5 times 10 to the power of negative 3. So the radius R1, so measured with the ruler, it's around 14 centimeter. So it's 0.14 meter. So R2 is also the same, 0.14 meter. So to calculate your moment of inertia, I equals to MIR1 square plus M2 R2 square. Around 1.37 times 10 to the power of negative 4 kg meter square. Okay? So I want you to do the same for your sample B. Okay, I think I forgot to give you the radius, right? So the radius from the center to your 20 cents, it's given by 2 centimeter only on both sides. So 2 centimeter SI unit is 0.02 meter. Okay, so if you look at the moment of inertia for both the sample, okay, even though 20 cents, if you look at the mass, even though 20 cents has higher mass compared to sample A, but the final calculation for moment of inertia, it's very obvious that sample A has higher moment of inertia. So that's why it needs longer time, okay, to complete the action because it is harder to be rotated as compared with your sample B. Okay, so what is the relationship between the moment of inertia and angular velocity? So basically, moment of inertia is inversely proportional with your angular acceleration. Okay, if the higher is your moment of inertia, the slower it is to accelerate in the rotation. So there is a question there. Okay, it's back to here for the 50 cents. Right. Okay, so for the 20 cents model, sample B model, if instead of using 20 cents, okay, if I am competing between two 5 cents, whereas one 5 cents I put it at the end, and one 5 cents I put it here. Then this one, versus this one at the end. Which one will win eventually? Okay, let's say this is sample A and this is sample C. So which one do you think will win at the end? So it's again based on your moment of inertia, right? So using the same method to find the moment of inertia, and eventually you will find this one has the lowest moment of inertia. So still the one that when it is nearer to the center of rotation, it will win. Okay? Because if by looking at the formula itself, even though mass affect your moment of inertia, however, the one that affects most is actually the center of rotation because of the R square. Okay? It has bigger effect. Unless it is your mass is very significantly different. Like if we compare a ping pong ball and a bowling ball again. Okay? The body is very, 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 very heavy. Okay, so in this case, the mass might be very significant as compared with the radius. But usually, it's the center of rotation that is better. Right? So now, look at this is my picture. The rotational kinetic energy. So, if we have three objects now, okay, see if I can find my object. Okay, these are the three objects. Yeah? We have one battery, one marble, and one ping pong ball. So, if I put these three objects on a ramp to go down the ramp. So if I move them to a ramp and three of them roll down at the same time. So can you predict which one will reach the bottom first? Okay, so which one will reach the bottom first? Yeah? Okay, so I need you to choose again. Okay, I want you to choose again. So, oh, not butter, it's battery. I haven't finished the Y. The A is battery, B is marble, C is ping pong. So which one will reach the bottom first? Oh, I should add an option. All will reach at the same time. It's taking longer than usual. And it's more exhausting. Yeah. Can they hear you? They hear me? I think so. And now I mute already. Just now when I asked him to stop that, yeah, I think they hear. I can't really take my mind. I said, oh, this is like, no one helping me, that's why I help you to talk. Okay. Okay, so I can see most of you choose marble. Okay, so now I want to show you a video where we have conducted this activities in the past tutorial. Yeah? So, okay. So these are the three objects: marble, ping pong, and the tree. Okay, so they are being put at the same height and released at the same time. Do you need it to be repeated again? Okay, I repeat again. So which one reaches first? It is the marble, right? Marble reaches the ground first. Okay? So why is it so? Again, it has to be based on calculator. So we as engineer, we always want to find the facts based on calculation. Okay? So okay. So have you seen the calculation on the Moodle? The one that I have uploaded? Back to Moodle again. Wait. Okay, going down, sorry, this is not your. So going down to your 1A here, you have velocity of rolling object proven by calculation. So if you click in this one, it will be prompt. Oh, okay. So these are the list of calculations that has been shown with different shape, right? Okay. So it's actually based on the potential energy, kinetic energy, and rotational kinetic energy. Okay. So back to our tutorial. So based on the data that we have collected last time, the distance that travel is 90 centimeter. Our ramp here, right? Okay. So bad matching it. So this is our ramp here. 90 centimeter is from the top until the bottom. So sample A is our battery. Sample B is the marble. C is ping pong. So we have also time for each of them 0.94 seconds for battery, 1.02 for marble, and ping pong use 2.75 seconds. So when we want to calculate the translational velocity, velocity equals to displacement over the time, isn't it? So 0.90 divided by the time. Okay, so you get 0.96. For marble, 0.88. As for the ping pong, it's 0.33. Okay, so this is the experimental data that we obtained. So now if we want to prove this the theoretical calculation, okay, so the theoretical calculation, usually we have our potential energy, we have our kinetic, translational kinetic energy, and rotational kinetic energy. Okay, just now you already mentioned, potential energy is mgh. kinetic energy is half mv squared. Rotational kinetic energy is half I omega squared. Okay, so the height of the starting point, okay, that we have measured is 0.37 meter. The mass of the battery has been measured as 24.24 grams. So convert to SI unit times 10 to the power of -3. Marble 5.54. Ping pong is 2.5 only. So when we measure the size, okay, the radius 9.88 times 10 to the power of -7. Sorry, no. The radius for battery is 0.9 times 10 to the power of -2. As for marble, 0.75 centimeter. Lastly, for ping pong is 1.9 centimeter. Okay, so you calculate the moment of inertia. Okay, so the radius for your battery is now, this is how your battery is rolling, right? So that is your center of rotation, so that is your radius. Marble, so this is the radius. Same goes with the ping pong. This is the radius. So calculate the moment of inertia. Yeah? For battery is given by solid cylinder. What is the formula for solid cylinder? Half mr squared. Right. So you get 9.88 times 10 to the power of -7. Right? So in order for you to find the velocity, okay, so use the mechanical energy. At the initial point on the top of the ramp, you have only potential energy, isn't it? When it is not moving. So when you reach the bottom, when you just reach the bottom here, there is no more potential energy, but left only kinetic energy and rotational kinetic energy. So if you apply in the calculation, potential energy, which is mgh, equals to kinetic energy plus rotational kinetic energy. Okay, simplify the equation. Moment of inertia for this one is given by half mr squared. Omega is given by velocity divided by r, right? This one is, if you remember the translation, between the linear and the rotation. E equals to R omega, isn't it? So move your R to the other side. Omega equals to D over R. Okay. So you can simplify your equation. Cancel off the M and cancel off the R. So you get half D squared plus 1 over 4 B squared. Okay, so your V is equal to root square of 4 over 3 times G times H. Okay, so the theoretical velocity here is given by 2.20 meter per second. Okay, so can you do the same for both B and C? Not to say them, I'm so tired. You know, no, because when you write down in the word file, no, maybe my surface too short and will hang out. This is heavy duty. Oi, oi, oi. 可以停快一点吗？要完了，要完了，你忍一下。呀，真攰咧，乖啦。我又唔識騎，你該將你。So sad. I want holiday so much. No, this is not. They say luckily they might extend one semester until June. Your book company. I find it myself there. They die me. 想到我，想到我。I've never been so sian before. The treat is a delivery. How come you can pick up that? Go to the main page or we have another page for review? Don't know. I'm a soft. Alvin, the formula, you do not need to memorize the formula. the formula, which formula do you refer to? The moment of inertia one, is it? If it is moment of inertia, no need, okay, because the chart will be given. But I think you might have to know the basic one. What is KE? Or KE equals to half mv squared. Rotational equals to half I omega squared. Okay, this one. And PE equals to mgh. Okay. The V equals to R omega here, yeah? Okay. It's the, just remember the, in your semester one, the translation. Yes, the relationship between the linear and the rotational quantity. Okay, so if you want to double check, you can. R it's in meter, omega is radians per second, which is the angle that you travel over the second. So when you cancel off the unit equals to meter per second, which is in your velocity. Okay? Yes, there will be a formula sheet. Yeah? The sample of the formula sheet, you can refer it in your Moodle. Under revision, under the midterm, or the partial midterm, at the very bottom there is a formula sheet, so you can refer to the sample there. Okay, so when you try your exercises, I actually encourage you to open, or if it is possible, just print out. If not, then you open on another page. So whenever you try your exercises, you can refer that as a reference. So that one will also make you to be more familiarized with what kind of things that you will encounter in your midterm also. Okay? Alright, so when you compare with the theoretical and your experimental, yeah, Do you get the same, exactly the same result? No, right? See, the value in lecture is different. However, the trend is similar. Okay, so the value the value of your velocity are different because of friction. Okay, because of the surface friction. The ramp that we constructed was actually the whiteboard. Okay, the back side of the whiteboard. If you look at the surface, it's made of wood. Okay, and it's not polished at all, so it's a very rough surface. Okay, so when there is a rough surface, the surface friction is actually very big. Okay, so if you look at the value, we have a huge difference between the experimental and the theoretical value. However, if you look at the trend or the sequence for the object to reach the bottom, it still follows. Okay, the trend or the sequence of the velocity is followed. Yeah. Okay, so whereas marble it's moving faster as compared to battery followed by ping pong. Okay. And the screen is not showing anything. Wait. What did you see? I want to try. Look like wait. Oh. How about now? Now can you see anything? Okay, sorry, thank you. If compared with online virtual classroom, right, I still prefer face to face. This one is like talking, and when it's okay. So we'll just continue here because of the situation. Okay. Let's complain, but let's try our best to learn. Yeah. So thank you for your feedback. Okay. So you can write down. Okay. So you can double check your answer with mine here. Right. So I will upload the solution letter also. Okay. So the explanation or the conclusion you can draw from here is okay, the value is definitely much bigger because of the surface friction, but the trend and the sequence of the velocity here is the same. Okay. Marble moves fastest, battery at the middle, and ping pong the slowest. Right? So any question up to here? We are ending our tutorial soon. Okay, the last part is the angular momentum. So you have two identical disks. This is stationary. So stationary here means your initial angular velocity for A is 0. So this is 60 radian per second. So this is initial velocity for B. So if each of them has a mass of 80 kg, this is radius. Okay, so A is moved towards B until it touches B. So A is not spinning, but it's moving towards B here. Okay, determine the moment of inertia of each is about the axis. This is the axis which passes through the center. So if this is the axis, then this will be the radius, which is equal to 50 centimeters. So you have to determine what is the moment of inertia. So moment of inertia of your disk A equals to mass of A. Sorry, this is a disk. So this is, what is the shape? It is actually the falling under the category of solid cylinder. Right? So moment of inertia of solid cylinder given by half mr squared. So half, the mass used now is 8 kg. Radius 50 centimeter, convert to SI unit is 0.5 squared. So 1.0 kg meter squared. Remember to write down the unit every time at your answer. Telling to do so, and if you forgot the unit, the half 0.5 marks will be deducted. Okay, so the moment inertia for D, because they are identical, so it's also 1 kg meter per second. So determine the angular velocity, the final angular velocity. Okay, so according to conservation of angular momentum, initial equals to final. So total I omega initial equals to I omega final. So initial, since we have two D's, right? So IA omega A initial plus IB omega B initial equals to IA omega A in final plus IB omega B final. Okay, so moment of inertia, IA equals to 1, omega A equals to 0, IB 1, the initial equals to 60 radians per second. So here, given by both of them stacked together and rotate with the same angular velocity. So your IA plus IB 1.0 plus 1.0 times with minus omega. Okay, so eventually you get a value of 30 radians per second. Okay. So any questions? If you have any question, you can always email or you can post on forum. Okay. So for the tutorial class for 2 3 effort, I will also stand by on Webex here. Okay. So whoever that needs consultation or when you read through the questions, okay, you want to have any assistance, you just log into Webex here and you ask. Okay, so I will also help you with your questions. But at the moment, I would like to call out for those who haven't have any booking yet. So you might want to step back, yeah? So we will try to see. Yeah, for the change of coin, yeah? Yes, I have already explained. Yes. Okay, so for the questions, let's say is it what you mean? Instead of sample B, if I modify the sample B, which is the 20 cents here, if I modify sample B, change the 20 cents to 5 cents at the center. Okay, so if you compare sample A and sample C now, sample C will still move faster. Why? Because the moment of inertia is small. Okay, the moment of inertia depending on the weight on both sides, the mass on both sides, and also the radius, okay, the distance between the center of rotation and where your mass is concentrated at, okay, where your mass is located. So if you look at here, this is only 2 centimeters. As compared to this one, from here to here is 14 centimeters. Okay, so definitely C will still move the fastest. Okay. Okay, so if you have no more questions, you may leave the room now. But for those who haven't have any grouping yet, please stay back, yeah? So we will discuss together on how to put the grouping to all. Okay, so I won't force you all in a group because later on you are the one who will be involved in teamwork. Okay, it's not me. So if I force you in a group and you don't know your team member, it's very difficult for you to work together. So that's why I need you to communicate first. At least before you are formed into a team, you actually ask the communicator, hey, can we be a teammate? Okay, so at least you meet the person or you have ever messaged him or her on the phone. Okay, so this is someone that you know that you can work together. Otherwise, if I force you in a group and somehow the member is perhaps MIA, uncontactable, you will have a hard time. No? Okay, so I want you all to stand back. For those who haven't have any grouping yet, please stand back. Yeah? 係啊，大嗯嗯。